Yeah, it's a real pleasure to be back. In this time, I'm sort of back with an idea that just got me my whole research program completely derailed about 3 years ago or so. It was at the end of a sabbatical, where I had, just this sort of basic idea that has been sort of a gift that's been giving since. And so it is a way to sort of think about these simulations of structure formation in the universe in a new, interesting way, I think. And so I want to walk you through that today, and I'll also show you, some of the applications that we can derive from this, and also give you a little bit of a sense. I think I only have one slide where we do an application of these new techniques in solving a plasma physics problem. And I'm rather excited now learning about astrophysical and terrestrial plasmas and see what those methods might be able to do for those calculations. Much of this work was done in collaboration with two former postdocs, Oliver Hahn and Raul Angulo. Ralph Kahler is a staff scientist at SLAC, an applied mathematician that we do a lot of the visualization with. So we've been writing actually papers for the visualization literature of how to do these types of visualizations on the GPU. And they are really amazing machines right now. We're drawing billions of triangles per second. It's a lot of fun. And Devin Powell is a graduate student now in the second year. And I'll show one of the cool things he's done recently. Yeah, so these cosmological Embody simulations, I don't have to say very much about it because you've seen tons and tons and tons. Many talks here, many of the local experts use them, and boy, do they turn out to be useful. We can sort of make predictions about clustering of mass in the universe. We've learned about the sort of density profiles we expect, and we look at these mass profiles and compare them with observations. We use them when we want to make predictions about weak lensing, strong gravitational lensing. Anything you can think of, cosmic velocity flows. They're just really nice to sort of have a virtual universe version to play around with and do your observations on your virtual universe first, so you can conceptualize of what you actually want to do with the real universe and the real data there. And so extremely useful. In a way, though, if you think about it, it's rather remarkable, actually, of how we often go about this, because, I mean, we do have 10 to the 67 dark matter particles in the galaxy if it were a 100 GeV elementary particle. Now, that is a big number. I mean, right? No kidding. Yeah? I mean, because between friends, we usually don't take it that seriously. You've got and then on a computer, in one object, we might be able to do 1 billion or 10 billion or so. Now, that sounds like a big number, but it really is not a big number at all. In particular, when you take the 6th root of it, thinking about that you're modeling something in a 6-dimensional phase space, 1 billion is actually a very, very small number. And so that's what I'd like to get to a little bit. However, fortunately, mathematically, nevertheless, if we have a Vlasov-Poisson system or a sort of collisionist-Boltzmann equation that tries to describe a density of sort of particles in phase space, and we plug in delta functions, back out comes the Embody system. So we feel very good about just solving the Embody system. But if you think about, and that's what I sort of want to go through a little bit today, is that we have many different codes in computational cosmology, but fundamentally they all make exactly the same assumption. The only thing they ever differ is how to evaluate the sum efficiently. That's really, in a nutshell, the only differences between the different codes. So they really don't check each other against anything. It's all, did they do a good job on this? And did they not take too large time steps so that the errors didn't accumulate? That's more or less where we're at. But it would be lovely to have other techniques that try to solve the same system, that we could convince ourselves that the solutions that we're getting are in fact the solutions. I mean, they look very converged, but are they the solutions to the system we're interested in, which in reality has a lot more particles than the ones we want to do. And so actually the problem that we are solving is usually we have some sort of softening, all these particles that get pushed around. We modify the gravitational potential because we don't want to have binary systems, triple systems, slingshots out. Obviously, dark matter particles wouldn't do that, right? two-body effects of 100 GeV particles gravitationally are negligible. And so what the simulations sort of crudely do is they just assume they have these fuzzy balls. So that's a density distribution that's actually modeled. And we can sort of think of that if you modify the potential, take two derivatives, that's the Poisson equation, it gives you the density distribution that that particle actually models. So they're unchanging round things that are mutually attracting each other and evolving in their own potential. So that's what our simulations currently are doing, and we know the results very well. We get NFW shapes. You hear many talks about halo concentration and many different things of how prolate they are, etc., how fast they're rotating, how they cluster. I don't want to spend too much time on this now, but just sort of say, first sort of walk you through visually what we have. Here's one example, sort of state-of-the-art in 1995, 256 cube simulation. You can do this on a laptop now. But what you see is there's a projection, right? So essentially in this image, every single pixel just counts how many particles do I have in it, and then apply a logarithmic stretch at the end, and that's your image. Project it down. So this should be actually very smooth because we took out one dimension, right? We projected the entire simulation volume into 2 dimensions. So that's like a smoothing. We integrate out one dimension. But nevertheless, you see it's just awful, full of noise. I mean, in particular, of course, all the low density regions, well, they don't have any particles in it. All the particles have the same mass. If it's low density, well, then you have very few particles per volume. And so I thought, that's a little bit of a pity, like a very noisy looking thing. And here is using our method. And what was the thing that got me so excited about this is that we didn't have to do anything new. I didn't rerun anything. I just took exactly the same data that we've had. And in fact, I had talked to Jim Peebles at a recent meeting. I was trying to get the original data from him from his sort of first 400 particles or so to try to reconstruct this density field from those, because you could literally do this with all the previous calculations, because we always wrote out the IDs of the particle. We always wrote out, okay, the integer associated, so we can track individual particles around. And that's the information that was in the simulations at all times, but we didn't use it, which is where did the particles come from? And so this is looking at this particle data as just, well, okay, there's a whole bunch of particles, they have this position. Here's what happens if we include the information where they came from. So we're going to walk you through how that works. But the exciting bit then, of course, was it now is a totally continuous field. There is no more noise at all. And what you notice is there's no smoothing. I mean, the contrast, in fact, went up. The information content wasn't sort of spread out and smoothed over. It's just recovering the information that was there, but we didn't appreciate if we didn't use the information of where the particles came from. Okay, and so essentially this very simple thing about this is that this idea that structure would form from a cold, collisionless fluid makes the initial conditions extremely simple, because the universe used to be almost perfectly uniform, tiny, tiny little density perturbations. But at every location in space, there's essentially only one velocity. The temperature of the dark matter is so low because the universe did so much expanding before structural formation happened that at one single location, you only have one velocity. That's the whole point of cold. Now, if you think about if you had a hot fluid, well, every location, think of neutrinos, right? There's a crazy amount of particles at the same location. They have totally different velocities. Some are barely moving relative to that point, others going relativistically that direction, that direction. So if you think about doing a simulation where potential is evolving and you have neutrinos, well, you have a huge number of initial conditions because the particles have all these random directions at every single location. They all make very different orbits. Cold dark matter is super simple. So you only have a single velocity. So what that means is if you think about a 6-dimensional phase space where you have your 3 spatial direction and 3 velocity directions, well, the velocity dimensions or velocity space is totally empty. There's one single sheet. I mean, sheet is sort of a 2-dimensional analogy. It's a 3-dimensional manifold, but it's at every single location, just one velocity. And so that was that very simple realization. oh, wait a minute, we don't have to do 6-dimensional anything. Like, we start out with a 3-dimensional thing. And then phase space evolves in a very nice way. This sheet can never cross itself, right? If it were crossing itself, that would mean I have two particles at the same exact location, the same exact velocity, in the same exact acceleration field, but they would move different directions. Well, that can't be. So this sheet will never cross itself, so topologically it'll look beautiful if you think about it in 6 dimensions. When you project it back into 3 dimensions, it looks like a total mess. That's probably one of the reasons why we haven't really done that very much. But the nice thing now is this very basic collisionless-Boltzmann equation describes how a density that just counts how many particles per cubic centimeter in cubic velocity unit would evolve in phase space. This is a pure advection equation, and we've studied it all and learned a lot where Liouville's theorem comes from, that it acts like an incompressible fluid in phase space. But it's now we can really think of a density that is a 3-dimensional manifold, delta function in velocity, moving through the 6-dimensional phase space. And so that's in a way it describes the continuum solution, right? Because now I have literally a density at every point, and there's no Monte Carlo aspect anymore that we had when we just pushed our little particles around. That just gets coupled with a Poisson equation, and then in plasma physicists like to call it Vlasov-Poisson system. But so all we have to do is evolve the velocity field, integrate out, evolve the density field, phase-space density, integrate out the velocity direction, arrive at a configuration space density, a spatial density, plug it into the Poisson equation, get a potential out. From the potential, we take a derivative, get our forces, and the forces now push our material around. That easy. Okay, this is a great assumption. I mean, we don't have that many dark matter particles if you want, but if you're interested in scales larger than a few hundred meters, there's no problem in defining F, right? And we're certainly, for many problems, interested in scales much larger than 500 meters in our galaxy. Oh, that's a really neat question that we should get into when I talk more about the new solvers. Yeah, it's sort of, but you certainly do want to, in this case, right, where n is so large, it is really the collective forces produced by many, many particles far away that dominates your force term. It's not the local ones that do. However, there are, in regions where you first fold this sheet in phase space, there's arbitrarily small scales that you could choose to go after, at which point you would have to use very small time steps to really solve the full system. And it's usually in those choices where you have you have to sort of pick the evil of what you want to do. There, you might still want to regularize the gravitational potential so that the problem doesn't have features on absurdly small length scales, which would inhibit you from calculating much further. And so it didn't fully go away. That's, in fact, a little pity. I said this in words already. The universe expanded so much, it really is just absurdly cold. And so this starting with a 3-dimensional sheet's a good idea. But it might not hurt to just think about it one more time, just in 1 plus 1 spatial dimension, where if you think about x velocity, simple phase space here, start with these initial conditions, no force acting. All that happens is that the particles that don't have a velocity, well, they will stay put, nothing happens for them. The ones that have maximal velocity, they will move them furthest, positive direction. Maximum negative or minimal velocity, they'll go over here. And what you see is just this typical multi-streaming in this collisionless fluid. In this one-dimensional line, they just penetrated through each other. And at any given location in the center, I have 3 streams at the same time. Okay? Well, that's fine. I just have to look at what's the density in this stream, the density in this stream, plus the density in this stream, and that gives me my full density at that one spatial location. So let's see, do I have that slide? Yeah. And so in a way, what we did is when we discretized this in the past with thinking about this with simple particles that had a certain kernel shape, what we had to do is pick a volume and then say, all right, how many particles are in here? Oh, okay, 3 in that volume. Okay, that gives me a density. Well, but it's an average density. It didn't give you an actual local density. You already averaged over this volume. And this, literally, it's that trivial. All we had to do is sort of think about, instead of having little cubes or spheres, just think about the line segments. Forget about that there's mass associated with the points. Just associate the mass with the line segment in between. It's that trivial, okay? If the line segment gets bigger, well, the volume's bigger, and that mass is distributed over a larger volume, so the density is lower.
It's not the same thing as just linear interpolation.
No, this is even less, actually. This is, for the density, in this particular explanation, it's just flat. Yeah. In fact, you know, it's actually the same in that sense, because in this case, all you can do is forget about the velocities, because all you're interested in were in real space, or how did that volume deform in real space. So it is, in fact, that delta x. That's true. It's not the length of this, right? It would actually be very funny computer length with kilometers a second on one side and just kilometers on the other. But the so you just take that length. That's how far apart they are, and that's the whole projection operator. There's nothing else to it. Interestingly, the velocities you can just get by linear interpolation. Right away, I know the velocity here, velocity here. And we've, in the meantime, do higher order interpolation, but that's sort of conceptually all that's going on. But the beauty is now I can pick any point here and just ask what's the density. Well, and then I count up how many streams are going through here, and then for every stream, I just find the density. And since the points started out on a regular lattice, it's even more trivial because the line segments all have the same mass. So just add them up, and it's better than an estimate. It actually gives you the entire microphysical phase space structure. I mean, it's just the 3 delta functions that you have. If I want the velocity distribution function at this point, well, it has 3 values, and you get exactly those 3 values. So there's no smoothing, no approximation there. Just measure the microphysical phase space structure.
The way you've drawn these lines, at the corners, you sort of know that's not right, in that the phase space density is too high.
Well, there it gets really interesting now. Yeah. So what I have a perfectly cold fluid, right? So there is no finite width to it. And so at this edge, you could sort of worry about, okay, you literally can have infinite density, right? Because delta x goes to 0. Yep.
We know that if you use the fact that the fluid does start with some finite velocity,
exactly, yeah,
but small, that tells you that the length and phase space between each segment can't get
absolutely. And the beauty is, because we have the delta x, you can always estimate the other. So, and since you know the initial phase space density, you can actually, that's regularized. It's not really a problem that comes up because, as we discussed earlier, we always will have sort of a length scale to close the system that we put in already. But another thing that you might notice here is if you do linear interpolation, you might be missing that point. And that's actually where all our current work is going on, is that we find that doing quadratic interpolation makes a big difference. And it's not surprising because orbits, if you just want to describe a circle, linear segments are never a good idea for that. But quadratic is already rather amazing. Okay. Anyhow, so it's funny because now we build up the whole density field really not by summing up invariant kernel shapes, but we literally follow that whole density distribution. So there's a lot more like having a grid versus sort of a particle-based method where you think of having values that you evolve and an interpolation scheme that you describe. That's how we do hydrodynamics in our sort of typical grid-based codes. And you sort of recognize the Embody technique, something more akin to what smooth particle hydrodynamics would do for the hydrodynamics case, so keeping all the, hoping to build up a smooth function from cleverly chosen kernels. All right, just one more time. I mean, boy, was I jumping up and down. This was bliss for weeks. It was images like this where we just sort of did a 2-dimensional slice through a 3D calculation. All these things we could never do. We could all of a sudden start treating it like, what I was used to, like analyzing hydrodynamics field, where I actually knew all the quantities, didn't have that whole noise anymore, and so it was just a real thrill. I already showed an animation. Fundamentally, so in 3 dimensions, all one has to do is to generalize our one-dimensional picture that we already have instead of line segments. We started out with a uniform lattice of points that were slightly perturbed to model the density fluctuation. So all we had to do is break up one little unit cube of this lattice into 6 tetrahedra. There's multiple ways you can do this. You just want to do it in a way that it's really a tessellation of the initial field. That means that none of the edges ever cross, right? So they really perfectly tessellate the space. And why do we pick a tetrahedron? Okay. It's the simplex in 3D, and it's sort of the simplest thing, and the volume's always defined. Imagine if I have a cube like this, let me take this vertex and put it over here. Please tell me the volume, right? And that's sort of you may have non-convex shapes because the object moves in the 6-dimensional phase space. You project it down, and it looks totally unrecognizable as an object. In a tetrahedron, what can happen, it can get degenerate. You have a point move through the plane made by the other 3 vertices, and that only happens in caustics. So it's great. It's a total diagnostic for us. And in fact, this formula, I only put this in the absolute only in because we want to have a positive definite density, but it's in the calculations or in the analysis, we can just track that when one point moves through the degenerate state, goes to the other side, we get a negative volume. So we can actually track every time one of these tetrahedra crosses a caustic. So it's another rather useful thing. Say again, please. Oh yeah, exactly. And so, in fact, it was a bit infuriating because a few days before we put our paper out, Seri Chandaran also thought of this, and he used a different one. He actually had one where you have 5 tetrahedra, 4 equal size, and the other one twice as big as the others. And we've actually played with that a lot because we worry about it for the simulation techniques, where you do the other diagonal. There's another way where you took 8 that are not a perfect tessellation, but they're perfectly symmetric. And so there's a lot of freedom, but surprisingly, it makes actually rather little difference. Yeah. Okay, so, but the amazing thing is, at the end of the day, this is like 2 lines of code in a way that sort of encodes this structure, is because all you have to write down is like all these vertices, and then you just write down sort of 6 4 tuples that describe how each tetrahedron is formed. That's your 2 lines of code, and the rest is really nothing particularly new. So it's very, very simple to use this in your analysis. And now, I mean, the really nifty thing about this was there is a problem that we've known for over 30 years, that if we study, do calculations where we start with a density power spectrum that has a small scale cutoff. So there's no fluctuations on some scale and below that. What always happened in these simulations is that you made all these funky clumps, all these sort of beads on a string would form. And for years, the rumor always had it, people, that's just because these guys start on a grid, and that's silly to start on a grid. And if you start on glass, this won't happen. But that had nothing to do with it. In fact, when you study it with the glass configuration or sort of more random configuration early on, you still get exactly the same number of beads in the same spacing. The reason is now completely obvious because take exactly the same data again, and you just notice that none of these filaments have any of these beads anymore. They're completely perfectly straight. The density is perfectly defined, and it's a very, again, very simple in hindsight. What happens is you're trying to model something that has sort of a constant density along here, right? But your particles are coming in, they're being compressed on one side, and they're being stretched on the other. If you think of your particles as isotropic objects, what happens is, well, they get compressed and then they move apart from each other. But if you think of them as isotropic, you have 2 clumps here. But because this is an anisotropic kernel, if you want, it now just perfectly captures that. And then, of course, we always, for anything, like you look at the density field, you should always think about the potential right away, because that's the input to the Poisson equation. And so, obviously, if the density field is free of artifacts, well, you want to use that density field to calculate your potential. In that, I mean, even in the first paper, I rant on about how exciting this is for the numerical simulation techniques. The other one you have to think. Oh, sure. This one is projection. So you have to double check there always. Exactly. And so in a projection, you always want to think about gravitational lensing right away, because you're doing a two-dimensional FFT on the same density field, and I'll show you an application of that in just a titch. Okay, but since I am jumping up and down, let me now do a slice only through the one of the objects in one of these simulations. Density field, velocity dispersion, kilometers a second, an entropy-like quantity because of sigma squared is like a temperature, and then we do density to the 2/3, just like we would use analyzing simulations of galaxy clusters. And here's the number of streams in the calculations. Goes up to 100,000. So that means 100,000 tetrahedra are overlapping here in the central point. And so the evolution in the center of these halos is extraordinarily fast. But what we can do is we can literally go to that single point, then look at, okay, there's 100,000 tetrahedra. Let me ask every single one of them what the velocity is at the point where I am. Every tetrahedron has 4 vertices. All of those have the 3 velocities. So I can interpolate exactly to the point I'm at and get the velocities. I draw it up in a histogram, and I get a velocity distribution function. But I also get it for the x and y and z components. That's great. A single point, I got the whole velocity distribution function. I'm not averaging over anything. Just that local point I get. It's exciting. No, you want to think of the corners now as massless traces. They just move around. The mass is all between them. Just like the line segments was, your particles now are markers. They just move with the flow. They just like random, not quite random particles, but some actual dark matter particles you picked out and just gave them a name. Yeah, it's 100,000 times here, and in fact, this sort of color bar tells you how many times. There's a single stream in the void. That's material just falling in. It's going up a few in these filaments, and you see multiple caustics in the filaments. And then the number goes all the way to 100,000 right in the center. In this thing, in cold dark matter, it just doesn't converge at all, right?
How large are the tetrahedras at the center? I mean, obviously, if you have an infinite or very large number of folding, then they're going to be very large.
Right.
Your estimate is going to be wrong.
I know, exactly. You want to describe something round, and all you've got is these crazy line segments, right? So, you really want to look at this the other way around first. Actually, you realize right away where your Embody simulation cannot track the microphysical phase-space structure anymore, right? So you can turn it around that way. Or in other words, there's definitely going to be some bias because you're obviously not mapping this correctly. Now, how good is the simulation, however? We don't know yet, and I'll tell you later a little bit of what we do now to do refinement in phase space to never lose resolution.
How large is, for 10,000 how large is the largest tetrahedron? Is it larger than the core and also?
Yeah. We can actually estimate very well. They're roughly the size of the initial mean particle separation. The way I know this is that here is 100,000 and here is 100,000. So I have 100,000 streams, but my density is 100,000 times the mean density. So on average, I expect to have the mean density, which means they separated by the mean particle separation.
But aren't they becoming more and more elongated?
Actually, the central ones have this funny one. Oh yeah, they will definitely make some random walk there. Like they'll get quite elongated, but I think because they.
The volume of the tetrahedron is the same, but the longest dimension has presumably gotten a lot longer.
I think it's at this point it's like random particles that make the four corners. So they'll go through all those configurations. You know, for the central ones here, you just lost the coherence completely. I mean, it really diverged. So I'm sure there's certainly some that sort of start getting stretched quite long, but the errors will build up very quickly, you know, of also separating the thin ones again.
Shape with time. I mean, I would have thought that you'd see something very much like, you know, just thinking about material falling in, right? Things on average get very long.
Yeah. But then when the other points come through again, they may diverge through the potential. It sort of depends really on your orbit structure you're on, because you know any non-harmonic potential will just keep having this phase shift. Well, a tetrahedron is made by four particles by definition. It's sort of four corners of the tetrahedron. Yeah. No, there's none inside, right? There's 6 times more tetrahedra than particles in the calculation.
I wonder,
Yeah.
I mean, that seems, I mean, I just wonder about how much you're affected by basically shot noise in the causing orbits to deform.
Yeah. So, I mean,
This is the, in a way, this is the a hard case to study. Have you tried looking at an equilibrium system where you start with something with a known distribution?
I'll show you for a few more examples. Because you know, I don't want to spend much time on it because I don't trust this stuff. I mean, we lost resolution. We're not mapping the function, and so you know, we don't want to spend much time on errors. We want to spend time on thinking about how to do methods that don't have those errors. I mean, I don't want to cut it short, but it's sort of. But the nifty thing now is, like, again, at single points, we're measuring the whole velocity distribution function. So if I go out about half a megaparsec, we get this distribution. Even further out, we get this one. And what you, of course, see right away is there is, if it were Maxwellian, this would be a parabola in this linear log plot. It is not, right? There's non-thermal tails directly. You see it's not even isotropic or a single temperature, even if you just go out a little bit. And the distributions, you know, get a lot more interesting, of course, the closer we get to the virial radius. No surprise. But it's all accessible, single points. And this leads to a very nice thing now, because we can now perfectly distinguish of what is a dispersion and what is a bulk velocity. Because the bulk velocity is just the mass averaged velocity at a single location. So at that location, again, we find all the streams. We know the densities in all the streams, so we can define now the mass averaged velocity at that point. And we're free of the dispersion. So the one-dimensional case, you look at this, and where we only have 1, 2, 3 streams here, you see this red line is the mass averaged velocity in here. So it gets close to 0. If I would have divided up the space between the particles in little pieces and just said the velocity is given by the particles on either side of that, I would get this ratty blue line. That's the equivalent of what Voronoi tessellation did, and which used to be the best estimator people have been using for at least a decade, which is shown here. And it just confuses everything because it doesn't know what the difference between a bulk velocity and a dispersion. And so you get all this noise everywhere where you have multi-streaming. And in our case, it just goes away. And this had this curious property that when we then study, of course, derivatives on top of this, we sort of realized that, of course, in our method, you notice that the sign and the magnitude is totally different for the divergence and also for the vorticity. I mean, this is very theoretical, but we like to think about this to sort of test analytic models for structure formation. And you just notice that the older answer was just wrong. And essentially what we've been doing is taking derivatives across caustics. And so conceptually, it just doesn't make a lot of sense. And so, it was quite exciting for us because we could define the divergence now perfectly and also the vorticity. And the vorticity now in single stream regions is perfectly 0. And that's, because the velocity field gets created by a potential, it cannot have a curl, right? And so that's what's finally consistent. In the old way of doing it, even in the single stream regions, one still would recover some vorticity, which is kind of nonsensical. On the other hand, this vorticity field, it's so useful in hydrodynamics to study vorticity. There's an actual transport equation. There's you can learn so much about a flow by focusing on this. In this case, I still don't really know how to make sense of it. All of it is some funny logarithm of the density weighted averaging of all the streams that one has at a given location. So that physical, I don't have much of a physical intuition. I don't really know what to do with that. So if you have some good ideas to explain this to me, I'd love to hear more about it. Here's a particular case where we just zoom in on one object, show the same quantities, density, vorticity, the divergence, and here just the vorticity in the or perpendicular to the plane that we're showing. And these are all models where we like to study cases where we do have a cutoff on small scales. So we actually have the resolution to sort of track smooth flow, right? That's a little bit the downside with cold dark matter. When typically we study that, we put in density fluctuations all the way down to the tiniest little scales. So even within a very short time, you already have lots of unresolved objects in your calculation. Whereas if we do some of the cutoff, we can evolve for a long time before we actually lose the resolution. Okay, so now the next thing then we did is like say, okay, is there sort of a quick and dirty way for us to put this into a code without changing very much at all, and sort of see what benefits we derive from having a better density field estimator? And the simplest thing we could imagine is just say, well, yeah, let's play through this idea where we keep our massless tracers being the vertices, and now we just say the mass is in the center of the tetrahedron formed by those 4 vertices. So what we could do is just, in a particle in cell code, very simply just say, okay, great, let's average the 4 vertices, put the mass there instead of at those corners. So now that gives us effectively 6 times more mass-giving particles, and it was very, very simple to program. And then we said, okay, let's try one order higher too, where we put 4 particles inside the tetrahedron and arrange them in such a way that they have the same quadrupole moment as the tetrahedron we want to model. It's another step up. And that was sort of a very quick way to not doing something very complicated of depositing this tetrahedral shape and making it overlap with the grid, right? And we just had to do define new particle positions. So very simple. And even that already was rather good. And so here is sort of a comparison of sort of a simpler problem now, where you have a plane wave that's a bit corrugated, so you have a second perturbation along this direction. Otherwise, it's just your plain Seldovich pancake. And we keep the same number of particles, but we increase the force resolution. And so our standard method, and you see how nicely this actually helps to do these smooth densities. You see all sorts of two-body scattering leading to a highly deformed tetrahedra that make the density field look so terrible. Sure.
How do we recognize the two-body scattering? What am I looking at?
It's sort of, so exactly. So I'm comparing the standard particle in cell technique with our technique. And the different cases all have the same number of particles, but ever higher force resolution. And what you notice is, in the ideal case, this should just converge to the right solution. But what happens is these two still look somewhat similar, but you see some noise appearing. But if you put up the noise even higher, all of a sudden there's sort of new trajectories that sort of happen, and that comes now because particles start feeling their own mutual attraction because we made the smoothing so small. That's essentially what this does. It changes the softening. Because there's a particle in cells, so the number of cells that's given here gives you the delta x of the softening. So across this, we have 512 points on this side, and here we only have 128 across it. And so the softening is forming about 2 delta x. But so we increased it 4 times here, and you already see that happening. And we can do that actually much more rigorously and show this in 1D, where you can do really an error norm between the analytic solution of Seldovich, which is exact up to shell crossing. And there we can just show how these errors become large very quickly. And so it was rather lovely that this very simple trick of just putting the mass in a different spot led to a nice convergent answer. Oh yeah, it's a very not particularly well, because it's a staggered mesh technique. I'm looking at Jim because he thought a lot about those. So staggered meshes where you have velocity defined at different points than the density. You always want to think carefully about the momentum. But nevertheless, the way we look at it is we don't want to build in conservation necessarily in the technique, right? What we're interested in is having high accuracy. Since it's solving the right equations, if I have a high accuracy, I will recover the correct solution, and I can use the momentum conservation actually to track how good the solution is. Yeah, I know. It's a funny thing though, because there's many folks that get so excited about their conservative technique that they often actually not recognize that they came up with one that has a much higher error than another one. And so, but yeah. Yeah. Yep. Yeah. And absolutely. So all these particles that are shown down here, they are the vertices that make up the tetrahedra that lead to these images. No, in fact, there's no. The particles that we track that get advected are the ones that make up the corners of the tetrahedron. In every time step, we say, okay, that's where my 4 points are. That means the mass is in the centroid. In that mass, we then deposit on the grid. That gives us a density. From that, we solve the potential. Once we have the potential on the grid, we differentiate it. We get accelerations everywhere. And then we interpolate those accelerations to the particle positions that make the vertices of the tetrahedra. And then we advect those. And so we all exactly the same steps as we always did. And we just only changed how we deposit the density field. And then we were there right away, aware, of course, that for the warm dark matter problem, this will help us a lot. So again, same thing, our technique, or our simplest version or implementation of this technique versus standard way, where we can see that many of these beads on a string effects are just gone. And so it's just, I mean, God, did we have a nice time on this. So anyhow, so let's look at a single halo forming in such a model. Right at the cutoff scale, the power spectrum at large scale is still the same as in cosmology, but just on small scale we didn't have a thing. And I still overdid it a little bit. I had a few beads form, but this is actually much fewer than the traditional method. And I still like to use this movie though, because it helps us visualize the trajectories that it goes on. And it's one thing that you should keep in mind, or you sort of see these isothermal halos of actually how these orbits, how little the velocities actually change in the center of the object.
So your initial conditions are taken out of a cosmological simulation?
Yep, this is totally cosmological. All it has a small scale cutoff, so there were no smaller halos before this one. And you sort of notice how you have 3 modes very clearly coming together, and these filaments sort of keep evolving a little bit like you might be that we might be used to from the Seldovich pancakes, where you sort of first make your caustics, and then the center keeps winding up. It continues making new caustics spreading at a time where also the outer caustics are moving out. So you see new lines appearing here. And I mean, you just get sort of a sense now of, it's really a fluid. It's not a sort of a noisy thing. Yeah, those unfortunately.
Perfect simulation. Would you expect any
No, none of these. These are all, these are spurious. In the traditional method, here I just overdid it a little bit with the softening length still. I really should do a version without them, but they can be useful now to track the orbits inside actually in the visualizations. And absolutely zero. And that is in fact was sort of a topic then of a paper we followed up with where we went a lot more extreme, up to 4096 cube particles, and really asked this question at the cutoff scale of such a warm dark matter scenario or any sort of scenario with a cutoff, is there any sort of nonlinear effect that creates a halo in a region where it wasn't like a density fluctuation to begin with? Like, potentially you could have thought, oh, there could be an effect like this. Turns out no. You literally every sort of single halo that forms is connected with a density peak that you heard early on. But your traditional method would have made, so here every circle sort of counts a halo. In here sort of outway, and you sort of see that there's a radical difference in how many halos you find. And the funny thing is, because now we have these filaments are resolved so perfectly, they have all these very dense sensors. So all of a sudden we also have to think about what is a halo. Because in the traditional way, artificial fragmentation broke up all these filaments in your standard halo finder, sort of friends of friends that just connects particles if they close, would claim these are the nicest halos in your box. That's obviously not what you want. And it is very sensible. If I want to find an object, I have to first sort of define what I'm going after, and it's always surprising. I mean, if it's extremely clumpy, then you get away with just doing friends of friends and not think much about what it actually was. I mean, that's of course very easy to fix. You just go to a somewhat higher linking length, a smaller linking length, higher density they require. You can study them. And then we literally actually were a little crazy. We went through this by eye and double checked also, what are the types of objects we have in different mass bins. And I mean, of course, you look at this, we put a cutoff at a few times 10 to the 11. I mean, this is not a model that the universe, I mean, this is long ruled out, right? But it's just, you really want to just think of it as a characteristic scale. And this is really invariant. I mean, whether we do this at higher redshift at lower masses, or in this case at redshift 0 at those masses. But what you'll notice is all the objects that you see below the cutoff mass, they don't look really like halos. It's very rare that you have something where you have some virial structure sort of appearing. All you see is these very funny caustics forming. But as you get to the higher masses, it looks just visually quite a bit more virialized. And so we now have to think a little bit about, if we do mass functions, think about what the predictions for galaxy formation are, of how to, which ones we should count.
So I should think of this more though as a solar mass at redshift 30 instead of
Exactly, or an Earth mass at redshift 80. Yeah. Exactly. Totally. Yeah.
But this is all new.
Exactly. Right. I don't have the number handy for an axion, but right. Exactly. Yeah. For WIMPs is around there. But and so when we did the mass functions now, it really depends a little bit just on our definition. But what we certainly did double check is that all those funny looking things at slightly later times, they all move very quickly to the higher mass end. So it's really, we didn't have a nonlinear effect that just created a halo there. And they only look funny, but they only look funny for a very short time because they then join the rest of the mass function. Yeah, so we were very excited, and I think that's sort of helpful for many of the predictions. So I have to be careful because I don't have a clock displaying here, so 10 minutes? Oh, okay. I was having too much fun. Anyhow, so the same thing then, density projections. We want to make predictions for gravitational lensing. And of course, with our perfectly smooth estimator, this little guy here, where our inverse magnification contour makes a little extra dip, that's real. Here, I'm not sure, right? It's just that density estimator is not that good, and so I don't know which wiggle is significant. Much easier to answer in this case. Well, it's certainly much easier than that case. And so I think there's a rather useful applications you can do with this. There's a recent thing my student Devin Powell has been doing, where we just applied for a patent for, where we can now take two polyhedra, look at their overlap volume, and calculate exact integrals across them, including for linear and quadratic functions. And I would have thought I'd just Google this and then download one of 15 options, but no. And so we had to sort of come up with this way. It's a very nice application of the divergence theorem at the end, volumes to faces, to lines, to corners. But it rather, in the 16 cubed cosmology simulation, I talked to you about the constant density estimator. This is just a linear density field. And we could even do quadratic functions that sort of have forms like this. And so we're currently applying this to look at the density distribution in voids and such aspects, which is, of course, much easier to measure here. Unfortunately, I don't have the particle plot with me, but you can already see from the triangles you see here that you would have barely any particles in those regions. It's exciting. It roughly is the Lagrangian volume. You go about 200 times the mean density. So it's just a factor of a few their mean spacing. In your first, that's your sort of first objects. And then depending how long you evolve this, you have many of these little guys evolve further. And so it's, if you overdo it, the whole box will fall in. So, right, exactly. Yeah. But, we're very well aware of it and make our boxes big enough so that doesn't happen. And so here's a thing we're just writing up where we apply the same thing now just in a 1+1 dimensional application to plasma physics, is Landau damping. So we model actually now a warm plasma, but we model it by a sum of, say, m sheets. And so now we broke up our velocity distribution functions in delta functions, and we make them model our Maxwellian to describe the worm. But the funny thing is we can also do it this way, where we actually break it up in sheets that start up vertical. And they then start tilting in phase space. And but now we can apply our same technique, right, including going all the way to 3 dimensions with this to study warm plasmas with techniques that are very similar to the codes that we have at the moment, and just study Landau damping. And what I'm showing here is an error as a function of the number of particles per cell that we use in the calculation. What you notice is we get the same error for the new method with about 40 times fewer particles than the number of particles with the old regular particle and cell technique. So for some problems, this is a relatively smooth problem and it's simpler, but I'm very excited about this, that there will be applications for this in 3 dimensions. And if we could really get a factor of 40 cubed savings, that's radical. It's really dramatic. So that part's really, there's a single mode here. And then in the paper we have some where I think we go like 18, 20 oscillations through. Actually, it just damps an absurd amount, but that's where we already use refinement in phase space. Not at all. No, in fact, it's just perfect because we're so smooth now. And right, and I'm just studying up on the language that's used to describe the numerical artifacts in the plasma case. And so in here, I just give you a few applications that we've been having fun with. And so if I still have about 5 minutes, then I just want to say I'm particularly motivated in developing this technique further and really try to do one realization as a first goal of a halo where we capture the entire microphysical phase space structure perfectly and where I can demonstrate that we converge to it perfectly so that there's a real error convergence for a single object. And it's related to this particular problem, actually, that in the 1990s, people were comparing hydrodynamics codes to do cosmology simulations of a galaxy cluster in this case. And they plotted the entropy profile. And there was more or less pretty much the only thing that some differences were seen. They seemed fairly small at the time, but there was one AMR code and a whole bunch of SPH codes and some grid codes that didn't go in very far. But there was a long discussion in the literature of what's wrong with AMR, that it didn't get that result. And so now there's a few new arguments that try to argue that it's slightly in between, that's a little bit lower than AMR. But for many years, doing high resolution studies, people realized is that the AMR result was actually the one closer to the truth, because SPH was lacking mixing. And it makes sense because you identify fluid elements with a certain mass thing. If they have different entropies, they can only communicate by actually having shocks or artificial viscosity interactions between them to change their entropies. So all that would happen is low entropy things would sit in the center and not be mixed in. Whereas in any fluid, unfortunately it worked for my coffee this morning, that when I put the milk in, it actually does sort of mix nicely. And so this became a big topic. Many papers, many fixes for SPH were written. I did one of them. I actually want to not spend too much time on it. But sort of mixing really is at the heart of this, of whether we have a power law entropy or whether we have a core in the center. And I just find it so amazing that there is a quantity for the collisionless fluids that's just the density of a sigma cubed. That's a so-called pseudo phase-space density. That's a perfect power law in all these simulations. And all I'm sort of, or my wishful thinking is that the hypothesis we're going to try to test is that if we now have a technique that is not discretizing in mass, like our technique where we follow these tetrahedra but now do refinement in phase space, which means all the tetrahedra get smaller and smaller mass, and we're now discretizing volume rather than mass. What I'm curious about is whether this perfect power law may in fact go away and we might have a core at least in that quantity. And well, until we show it, but that's the motivation why you would really want to keep pushing on it. Because of course it's kind of, we probably get too much worked up about the centers of dark matter halos and the NFW profile, cusp versus core, because there's so much baronic physics going on in there that it's not clear that we really have any observational handle on this. But from a theoretical point of view, it certainly will be nice to have one representation that sort of settles whether this continuum solution will do that. And so for this, we do refinement, so same simulation. Here ends up with more and more vertices. And we'll also do this now with higher interpolations, where originally we just did a linear tets. So you start with a little cube that you had vectored in an external potential, and which is rather good because we don't need a lot of nodes and we already get a very nice density distribution. But with these quadrilaterals plus refinement, it's just beautiful. And here is a crazy Embody with a huge number of particles, so you don't see any noise until the very end, just as a comparison. And so it's this technology that we're really excited about. But I mean, this is some of the hardest things we've ever done. I mean, to get high dynamic range on this, to do the deposit, to do the multi-scale gravity, to do the multi-time stepping. So you have adaptive time stepping on the small scale. There's many issues here that we had hoped could possibly be a little bit simpler. Anyway, thanks so much for your time.